So thank you all for being here. Like I said, my name is Samuel Lobert, and I'll be presenting my paper, Common Reference Potentiostat for Reducing Interference in Simultaneous Multi-Technique Electrochemical Arrays. And if you're all here today, you probably know how impactful electrochemical sensing can be. And one of the reasons for this is that it gives us a high selectivity and sensitivity for a multitude of different analytes. And that's because with different electrode materials or different electrochemical techniques, we can selectively sense multiple different analytes. And especially, we're getting into a focus on arrayed platforms, so where we can detect these simultaneously at one time. And with the arrays, we can fabricate multiple electrochemical cells in a lab on CMOS or microfluidic platform. And this allows us to create portable point of care sensing systems. It allows us to only require a very low sample volume of our analyte solution. And we can do rapid high throughput testing with just a very small device. So for an example, you can consider blood analysis. You can see we have multiple different electrochemical techniques like chronoamperometry, differential pulse voltammetry, and electrochemical impedance spectroscopy. And these are used to selectively sense different analytes such as lactate and glucose, to everything such as like pathogens as bacteria and viral antibodies. And so looking at the literature, we see a lot of simultaneous and pseudo-simultaneous examples of electrochemical sensing. But the main difference here is that a lot are actually the pseudo-simultaneous sensing, where we do time division multiplexing on our different electrochemical techniques. So I don't know if you're too familiar with these techniques, but often like EIS can take a very long time to do, and sometimes for our CV and as well. So completing these different tests can take a very long time, and it's not what we want. We see other examples that are true simultaneous systems, but they're only single technique. So you can see we have our electrode array, but we're applying the same test to each of these. This gives us very high resolution electrochemical sensing spatially, but it doesn't allow us to do the multi-technique operation. So our goal is to establish truly simultaneous multi-technique electrochemical sensing. And you can see here, we'll have a multi-channel potentiostat where we can stimulate different cells in our microfluidic channel with different electrochemical techniques at the same time. The main challenge with this, though, is that you have to remember in the liquid-based systems, we have our analytes in a conductive electrolyte background medium. So each of the electrode cells are going to have a different potential on them. And so how do we understand the interference between them and potential crosstalk that we might see? The first thing that we decided to do was take a commercial potentiostat, CH Instruments device, and we conducted a CA and 1 millimolar ferrocene as our control case, and you see we get a very expected chronoamp kind of measurement. But what happens when we take another CHI device and try running a multi-technique measurement? You can see I start my CA, and then about 5 seconds later, I start a CV measurement downstream. And as soon as I start the cyclic voltammetry measurement, I measure massive oscillations on my CA channel. So this is really bad from a sensing point of view because we're not at all what we would expect to see. So why is this happening? And to understand why it's happening, we really need to jump into the traditional potentiostat circuit topology. And so what you see here is what I'm calling the common working electrode potentiostat. And the common working is a naming convention where we're going to name the electrode common that we're going to place at analog ground. So looking at OPA2 here, you can see that how the operational amplifier works as long as we have negative feedback, there's going to be the virtual short condition, which places our analog ground at the non-inverting input at the same potential as our working electrode. Then if we go up to operational amplifier 1, we're going to see that its negative feedback loop is going to be established between the solution resistance, between the counter electrode and the reference electrode. And in order for our electrochemical experiments to be well understood and valid in a sense. What we really want is that no current flows through the reference electrode. What this allows us to do is that we have a stable known reference, and by having no current, we're ensuring as little as possible that electrode will change potential during time of the experiment. And in order to ensure that there's no current that flows through the reference, what we do is we attach it to the high input impedance node of the op amp, and to allow that condition to be present. So why does this fail when we move to simultaneous multi-technique operation? What we see is that if we use two different electrodes, which is common in each of our cells of our channel, that we have a solution impedance from the background, which is connecting both electrodes. And in this case, we will have current flow because the stimulus potential on the first cell is not equal to the stimulus potential on the second cell, which disrupts the condition of not having current flow in the reference, as we claimed on the previous slide. Then, if we use a single shared reference electrode, which is very common where you will use a non-polarizable reference electrode, such as silver chloride downstream or something like that, what we're trying to do then is apply two different stimulus potentials to the same node. And I mean, consider two different batteries wiring them in parallel. Obviously, you're going to have an undefined potential on that node. And what this really means is that in both cases, we have connected negative feedback loops, and they're not going to be stable. So hence, our electrochemical experiment is not going to be valid. So what we did was use the common reference potentiostat, and we then apply the analog ground potential to the reference electrode, so the reference electrode is stable. And what this does is there's no longer a potential conflict on the reference electrode. In the case that you're using multiple reference electrodes in your system, now they're both at the same potential, so no current will flow between them. And if you're using a shared reference electrode in your system, then again, they're both going to be at the same potential, and you're not going to have that conflict. If we design the operational amplifiers in OPA4 and OPA3 to allow negative feedback to occur correctly, which is not too big of a challenge because the electrochemical change that we're going to get on our working electrodes is going to be very slow because they're electrochemical processes, and our op amps are high-speed devices and are able to catch up and be stable. But in that case, we can apply our stimulus directly to each working electrode at different potentials, and we can read out the current at both of these points as well. So the first thing that we did was try to mimic the experiment from the previous case with the common working setup, and you can recall the oscillations that we saw before. When we implement our common reference potentiostat in just an electrolyte, so we used a phosphate buffer to just look at the ionic current moving between and get rid of any electrochemical like redox processes that are taking place. We set our one node at 0 volts to just say nothing should be happening at this electrode electrochemically. And then at our downstream channel, we applied our cyclic voltammetry. And in this case, you can see that we removed all of our oscillations, but we do see still about 7.5% current crosstalk on the CA cell from the downstream CV cell. We're still working on removing some of this crosstalk. We expect that if we optimize the electrode geometry and introduce guard rings in the system, that we can hopefully further take this down. We then said, okay, well, what happens if we introduce a redox probe into the system to verify that we can electrochemically conduct two simultaneous measurements? And so we conduct a CA at 0.8 volts with a ferrocyanide redox probe, as well as a cyclic voltammetry test downstream. What we see here is that we, again, no longer have the stability-based interference that we saw with the traditional common working potentiostat topology. And although we do still see a little bit of the crosstalk, we get the expected measurements in both cases. As a conclusion, We discussed the typical like simultaneous sensing approaches that we see in the literature and analyzed how the traditional common working potentiostat fails when we move to simultaneous multi-technique sensing. We then introduce the common reference potentiostat and show how, although we still get some intracell crosstalk in the system, that we do remove all of the instability and we're able to conduct our measurements as we would want to. And as I mentioned before, we're undergoing the future efforts to remove the crosstalk. I would like to acknowledge the National Institutes of Health for funding this research and my research team at Michigan State University for helping me make this possible. And I'll now take any questions.